Last video, we finished up looking at the angular parts of our hydrogen wave function, and we essentially solved for um, those angular parts were equal to what we call our spherical harmonics, which are equal to uh, -1 m plus the absolute value of m over 2l plus 1 over 2l minus the absolute value of m factorial divided by l plus the absolute value of m factorial, all square rooted, times these associated Legendre functions of cosine theta, times e to the I m phi. So these were our spherical harmonics. They essentially were the angular solutions to our hydrogen atom, and we looked at how they're essentially the eigenfunctions of our L squared, our angular momentum squared operator, uh, with eigenvalues L plus 1 h bar, and as well as the LZ operator with eigenvalues of just whatever that M is. And we looked at these, and that essentially captured all the angular parts of our hydrogen atom. What we're going to do now is we're going to look at the radial part of our hydrogen atom. And to do this, we're going to have to consider the actual potential that the electron that is experienced between the electron and the proton in the hydrogen atom. And our goal is going to be essentially solve that equation, that differential equation that when we were doing our separation of variables, we derived, um, which is this one. Uh, Forgive having to watch me write this all out. R plus this a squared is, now that we've solved the polar part, we know that that separation of variable constant was just this L times L plus 1. Um, and this was all operating on what our radial part of our wave function was, and that equaled the energy of our atom. So what we're going to do is we're gonna put in the form. Right up till now, we've only been discussing just any general central potential. We're going to actually look at the Coulomb potential that is that proton and electron experience, and we're going to solve this differential equation to sort of get our full three-dimensional hydrogen wave function, which is just our radial component times that angular component. So what is that Coulomb potential? Well, we can stick, rather than sticking strictly to hydrogen, we can generalize it to hydrogen-like atoms. But so it's E squared, the charge, over 4 pi epsilon naught times R, where this Z here is just, we can scale the charge of the nucleus essentially. If you have say an ionized helium atom or lithium or something like that, where there's just that one valence electron, the nuclear charge is going to be slightly different. You can just multiply it by the Z to scale it. But in general, the Coulomb potential for a hydrogen-like atom looks like this. So if we substitute that in for our potential, do a bit of chain rule on that term there, this differential equation ends up being the dr squared plus 2 over r d dr. Um, and, this is operating on our radial wave function, plus 2 mu over h bar squared. All times, done a bit of algebra and brought everything over to this side. Z e squared 4 pi epsilon times r minus h bar squared L plus 1 all divided by 2 mu r squared, that acting on a radial function, all equal to 0. Now, so this is the differential equation we're going to solve. We can, make this, we can define some dimensionless parameter, we'll call it rho, which is just sort of a scaled distance rather than, make this a dimensionless quantity that's proportional to the radial distance or that radial component. And then, our radial function we're going to try and solve for is as a function of that. And we can again recast this differential equation in terms of 1 over a squared, b squared, d rho squared, r plus squared dr d rho plus 2 mu over h bar squared e plus z e squared 4 pi epsilon naught r minus h bar squared L plus 1 over 2 mu a squared rho equal to 0. And you can see sort of another thing you can do is look at these sort of coefficients to these terms in the brackets here. Sorry, forgot to switch this one. The coefficients in these bracketed terms here, and we can define two more quantities. A is just going to be equal to 4 pi epsilon naught h bar squared over mu ze squared. It has dimensions of length, and we can define some dimensionless energy parameter we're going to call gamma squared, which is just E over h bar squared over 2 mu a squared. So defining all of these things, we can sort of clean up this whole messy differential equation here with all these terms. And again, all we've really done is some substitutions, some algebra. But the differential equation we finally end up with ends up looking like this. Rho dr d rho plus negative gamma squared plus 2 over rho minus L times L plus 1 over rho squared times R equal to 0. So this, this ends up being the differential equation we're trying to solve. Again, we're doing it in terms of rho, which is just some dimensionless parameter proportional to the length, and we've also defined these sort of a length scale for our problem and a dimensionless sort of energy scale there. Now we're tasked with trying to solve for that radial, this R function. So let's do that. All right. One of the things we're going to look at though is some limits here, right? So if we go to really large rho, what do we expect, right? Well, all of these 1 over rho terms and 1 over rho squared terms at large are essentially 0, and this differential equation reduces to the second derivative with respect to rho minus gamma squared times r is equal to 0, or, more familiar perhaps to some of you, this is our differential equation, which is a pretty straightforward one we've solved. This is just going to be an exponential. It's going to go, r is going to go as e to the plus or minus gamma rho, right? The issue is we need this, our R function to be normalizable. So the positive term here, that blows up at large R. So we can't use it. And essentially we know that that R term is going to go as negative rho e to the negative gamma rho at large R, right? We can also look at, where rho is small. And in that case, if we look at this term in brackets, for small rho, these two terms, just this 1 over rho squared term is really going to dominate. And essentially that bracketed term is going to go as L plus 1 over rho squared. So if we look at this small rho region, our differential equation reduces to d squared r d rho squared plus 2 over rho dr d rho minus L plus 1 over rho squared r equal to 0. And at small rho, that's sort of the differential equation that we're looking to solve. And just by inspection, we looking at that differential equation, if we have rho to some integer q, this can solve that equation, right? If we look at this, the first derivative with respect to rho of an r that goes like that is just going to be q times rho q minus 1, and the second derivative would then be q minus 1 times rho to the q minus 2. And if we plug both those back into our differential equation, we end up with q minus 1 rho to the q minus 2 plus 2 over rho q times rho to the q minus 1 minus L plus 1 over rho squared times rho to the q is equal to 0. And this rho is going to make that q to the minus 2. We can factor out that rho to the q minus 2, right? And we end up with q minus 1 plus 2q minus L times L plus 1. All of that times rho to the q minus 2 is equal to 0. So this sort of, for small rho, we expect our function to look like that, provided that this term, provided that is actually equal to 0. And if we look at that, this ends up being just the equation, we can expand that out and everything, and we get the quadratic equation L plus 1 is equal to 0. If that's true, that has two solutions. One is q equal to L, and the other is q equal to negative L minus 1. Now, right, if we can sort of determine which one of these is good, again, we have to have this be normalizable, and we're looking at a function that goes as rho to the q. So if we look at this, rho to the negative L minus 1, this is going to blow up for really small rho. So this solution here is not sort of the one we're looking for. We're expecting at small r, our r function to go as rho to the L, right? So for small rho or small radius, we expect it to go like that, and for large radius, we expect it to go something like that. So that's essentially what we've got. We know we can just put these all together, and we're expecting our function of rho to sort of go as rho to the L times e to the negative gamma rho times some other function of rho that's going to sort of connect these these parts of the function that are going to dominate at small r and then at large R. And this is going to be the function that we multiply with it that sort of connects the two and describes that intermediate range. So with that sort of form of our radial function, if we plug it back in to this differential equation we're trying to solve, we're going to need, the second derivative of it, the first derivative of it. We can, sort of chain rule the derivatives on this function, do a bit of calculus on that, plug it back in, do a bunch of algebra, very tedious. I'm not going to, make you watch me run through this right now. You know, maybe I'll make you guys all do it. You all do it as a homework assignment. But the punchline is after you've taken the derivative of this, taken the second derivative, plugged it in sort of organized terms, we end up with a differential equation for that h function, d rho squared, that looks like this: plus 2L plus 1 minus gamma rho times the first derivative with respect to of h with respect to rho plus 2 1 minus gamma L times that h function again is equal to 0. And we now have sort of the differential equation that we're going to solve for this h function. And then that'll give us our full radial wave function. And the way we're going to go about this is just a sort of a power series expansion where we're going to say rho is equal to the sum, we'll use j equal to 0 to infinity of some coefficients times, a rho to the power of j. The derivatives, we can figure those out, right? dh d rho is just going to be sum over j equal to 0 from 0 to infinity of j times cj rho to the j, which, that first term, j equals 0, is going to be 0. So this is going to be sum over j equal to 1 times infinity cj times, whoops, forgot that j times cj rho to the j. I also forgot that minus 1, j minus 1. I can then shift these indices, right? And just say, well, this is equal to rho of j equal to 0 to infinity of j plus 1 times cj plus 1 rho to the j, right? The second derivative of that then, sorry, a little far. Second derivative of that is then going to be sum over j equal to 0 to infinity of j plus 1 times j cj plus 1 rho to the j minus 1. And that's what our second derivative is. Plugging these back into our differential equation up there gives us just the result sum for j equal to 0 from 0 to infinity. J plus 1, cj plus 1 rho to the j plus 2, L plus 1, sum over j equal to 0 to infinity, j plus 1 times cj plus 1 rho to the j minus gamma, minus 2 gamma, actually, sum j equals 0 to infinity, j cj rho to the j is equal to 0. forgot a term in here. Sorry about that. Um, Plus 2 times 1 minus gamma L sum over j equal to 0 to infinity, Cj rho to the j equal to 0. So we have that lovely thing. You know, all of these are in terms of rho to the j. For this to be true, the coefficients of all of those terms, we factor that out. All of these coefficients have to be 0 individually, or essentially j plus 1 plus, times Cj. Blah, getting very sloppy here, trying to rush. J plus 1 times Cj plus 1 plus 2 L plus 1 J plus 1 times Cj plus 1 minus 2 gamma J Cj plus 2 1 minus gamma L Cj. That has to be all of these coefficients, or this equation has to be 0 individually. And this gives us our recursion relation for those coefficients, those CJs in our power series expansion, in our power series function. So if we do that, bring all the CJ plus 1s to one side and sloppy to one side, and we end up with Cj plus 1 is equal to 2 gamma J plus L plus 1 minus 2 all divided by J plus 1 times J plus 2L plus 2 all times Cj. So this recurrence relation tells us our Cj's in our expansion, our power series form of that function, where we're summing from j to infinity, Cj times rho to the j. So that's how we define our coefficients in this function. It may seem like we're done, right? We've got a recursion relation for our coefficients, and we've got the form of that h. Multiply it by the plug it back into the thing we had at the start, and we've got our function. But we have to be careful, right? If you remember when we were looking at that angular part of our wave function, we had this power series solution, and we had to truncate that series at some maximum value because our wave functions require certain properties. We have to do the same thing here. We have to make sure that this function doesn't blow up in the limits that we expect. So we have to kind of check everything, and what happens as j goes to infinity, right? And if we look at this, well, this term in brackets here is essentially just going to be j. Likewise, this term in the bracket and that term in the bracket for really large j are essentially just j, right? So this, for large j, our Cj plus 1 is approximately equal to 2 gamma j minus 2 over j times j, so essentially just j squared, or this is essentially just 2 gamma over j times Cj, right? Now, if we plug that into our function, our power series here, this tells us for large, when j is really large, this ends up being, well, the first term's just j equals 0, so C0, and then we get C1, which is just going to be 2 gamma over 1 times C0. The next term is going to be, C1, which is 2 gamma, that's a 2, sorry about that, times 1, C naught times the 2 gamma over 2 again, 2 gamma over 2. being silly here, times rho to the 1 times rho squared. And then the next term in that series is again going to be the 2, 0, 1 C naught 2 gamma over 2. That's my, so this is C0, this is my C1, this is my C2, this times another 2 gamma over 3 this time from the recursion relation is my C3 times rho to the 3 plus dot dot dot. You can sort of see this pattern here. You can factor out that C naught and you end up with 1 plus, I'm just going to call it alpha. I'm going to define alpha is equal to 2 times gamma times alpha times rho plus alpha squared over 2 factorial. And then this is going to be alpha times rho squared cubed times rho cubed over 3 factorial plus dot dot dot. And we get this whole term where this, if you, hopefully you recognize this, this is an exponential of, 2 gamma, well, it's just alpha rho, but 2 gamma times rho. This, what we see is this function blows up if we take it all the way out to j into infinity in that. So we have to truncate it at some maximum value of j, and then we'll have the function we want, which will be sum from j equals 0 to some j max of cj rho to the j. And then that will be what we need. So the question now is really quickly, what is j max? To figure that out, we just look back at our recursion relation, right? We have C j plus 1 is equal to 2 gamma times 1 plus j plus L minus 2 all over j plus 1 times j plus 2L plus 2 all times Cj. So if I have some Cj max, right, if I make this I'll just use M for now. Cj max, this term above it has to be 0. So to do that, essentially this denominator has to be 0. I have 2 gamma, 1 plus j max plus L minus 2 is equal to 0, or 1 plus j max plus L is equal to 1 over gamma, right? Now, everything on this side is an integer, so this has to be an integer as well. And we're just going to call that integer n. And this is our principal quantum number, is what it's going to be called. So we essentially have that there is some principal quantum number that is equal to 1 plus our maximum value for j plus L, right? And that's sort of how we decide where we have to truncate that power series. Now, a few things that are worth noting about this. All right, the first thing is J and L were both of these terms were they were from power series. Those are expansions where we were summing from 0 to up to some higher value. So the minimum value, these could both be 0. So n, that integer, actually goes from 1 to 3. It starts at 1 is the lowest value. It can never actually be 0. Another thing is just from what we just showed, that this n is equal to 1 over gamma. And if you recall, we defined, this gamma comes from our original differential equation where this negative gamma squared was sort of a dimensionless sort of energy parameter that was equal to E, the energy, divided by h bar squared over 2 mu a squared, right? So, replacing this with our n, this is equal to negative 1 over n squared. So we can solve for that energy, and our energy of our hydrogen atom, our system, is going to be equal to excuse me, negative h bar squared over 2 mu a squared times n squared. So it's going to involve, that energy is going to involve that principal quantum number. We also had defined a, this length, as 4 pi epsilon naught h bar squared over z mu e squared. If we plug that back in here, we end up with the energy is equal to negative mu all over 2 n squared h bar squared times z e squared over 4 pi epsilon naught all squared. And we've got the energy of our hydrogen atom. And like many of you've probably seen in previous classes, it goes as 1 over n squared, that principal quantum number. Lastly, just circling back to this, so we have some energy level defined by that principal quantum number n that determines what our maximum J value is, right? So we have, sorry, let's just scroll down. So we have some n that's equal to J max plus L plus 1. So L can go from n minus J max minus 1. N can go from 0 to infinity and all that, but the upper bound on our L ends up being occurring when J max we go to 0. Sorry, so the largest possible value of L we can have is n minus 1, right? So our L values can go from 0, 1, 2, dot, 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 all the way up to n minus 1, right? So we've sort of got, you know, our quantum numbers that we've come about here are the principal quantum number, which is just 1, 2, 3, dot, dot, dot. And this sort of indicates the energy level we're in. Our L quantum number can go from 0, 1, 2, all the way up to whatever our n value is, minus 1. And then that m quantum number that we had from that azimuthal part of our equation can go from negative L all the way up to positive L. And these, just going through the solutions of our wave function, sort of define the quantum numbers where, depending on previous courses, if you took 203 and some atomic physics or anything, you may have seen these and be familiar with them. We've just sort of derived those. Right. So a few more things about this energy up here. Right. Sorry. We can write that energy a lot of ways, and essentially, so we've got E sub n is equal to negative 1 over 2n squared times Z E squared 4 pi epsilon naught all squared mu over h bar squared, where n is our principal quantum number, going from, can be 1, 2, 3, essentially any positive integer up to infinity. For the hydrogen atom, Z is equal to 1. There's just a 1 proton for the nucleus, and we can approximate that mu, if you recall, that was our sort of effective mass, which was the mass of electron in this case, times mass of the proton, times mass over mass of the electron plus the mass of the proton. Well, this is approximately just the mass of the electron times the mass of the proton over the mass of the proton, or the mass of the electron. If we take that sort of approximation, this energy can be just rewritten in terms of, the rest mass of that of the electron, and this becomes negative 1 over 2n squared, that rest mass of the electron times E squared over 4 pi epsilon naught h bar c, all squared. And we can define this term as alpha, which we call the fine structure constant, which you may have heard of. It's essentially just a strength, measure the strength of the electromagnetic coupling. It's also called the electromagnetic coupling constant. It's approximately equal to 1 over 137. This rest mass of the electron is 0.511 mega electron volts. So we can write the energy in terms of those units, in terms of those constants. And so in that case, E sub n is equal to negative 1 over n squared, 1 half alpha squared me, the mass of the electron, c squared. So we can write it in terms of that. Another way that you might be very familiar with is if we plug in all the values for those constant, that we can write the energy of the hydrogen atom energy levels as negative 1 over n squared times what we call the Rydberg 13.6 eV. So this is probably familiar if you had any, you came about through physics the same way I did. That was a common way I saw these being written. These are, we made some approximations here, and these, energies are accurate to within about 1 part per thousand, which is not very accurate, considering how well we can measure things. Another thing is that length scale that we wrote in hydrogen, that A, for hydrogen, this, 4 pi epsilon naught h bar squared over me squared. This is the Bohr radius. This is 0.0529 nanometers, and kind of gives us the length scale of our atom, and written in terms of that, the energy levels of the hydrogen atom are negative 1 over 2 n squared times 1 over 4 pi epsilon naught a naught squared over e squared. So you may have also seen that the energy levels written that way. These energy levels are also degenerate, right? For each n, we have those different possibilities of quantum numbers. There's L states, and then there's M states, and then there's actually spin degenerate states, and that. So for any given, so there's all sorts of these degeneracies. I'm not going to go through, the textbook discusses them in a bit more detail, but the gist is there's several degeneracies for each n that are related to sort of the symmetry of the problem we're looking at. The Coulomb potential that we were using to derive this is spherically symmetric, and that leads to these degeneracies, right? We looked at all of them in terms of the angular momentum and degeneracies with respect to that. All of that comes from the fact that our potential that we're solving in that has a symmetry to it. You can actually break that symmetry by applying, electric or magnetic fields, in which case these degeneracies get broken and you see a splitting of those. And we'll discuss some of those later in the semester. Anyway, we've discussed a lot today. We've sort of derived these energy levels, the principal quantum number, how it relates to other quantum numbers, and we've sort of sorted out the radial part of our wave function. Next video, we're going to put them all back together with those spherical harmonics, get our full hydrogen wave functions, and start to discuss, just start to look at that and make some calculations on what you might expect for time evolution of hydrogen atom in a certain state and things like that. So if you have any questions, email me, bring them up in our synchronous sessions. We'll discuss this a lot more. And I will see you next time.